If you were part of a project development workshop we had a long time ago, middle of last year, it had a different name at that time. John Bates facilitated that workshop, if that jogs your memory. It was called Modelling the Impacts of Cascading and Compounding Natural Hazards on Built Environment at that time, but it is the same project. My name is Blythe McLennan. I'm a research manager at Natural Hazards Research Australia, and I'm here with my colleagues Varna and Nicola, also here from NHRA. So I'll kick off with an acknowledgement of country. So I want to acknowledge that we're meeting across a range of different Aboriginal lands today, and that we're guests on these lands. I'd like to pay my respects to elders past, present and emerging, and also recognise that these lands and waters have always been places of teaching, research and learning, and that sovereignty has not been ceded. So today's briefing has two aims. It's to introduce a research team and introduce this project to you, and give you a chance to ask questions of the research team, and provide feedback and your thoughts on the approach the team's proposed to take and the intended outcomes of the research. And then the second aim we have is for you to have an opportunity to tell us if you're interested in being involved in this project moving forward and how you'd like to be involved. The briefing's sort of half-half. The first half will be a presentation from the research team, and then the second half will be a chance to have a discussion and ask questions and get your feedback on the research, the second half of the briefing. As you will have seen, we're recording just the presentation part of the briefing, not the discussion, so that we can share the presentation with others who weren't able to join us today. And that presentation, we'll actually put it up on the project webpage so it can be shared with others. Following the briefing, Varna's going to share a little poll with you that will give you a chance to let the research team know how you'd like to be involved in the project. So we'll share it in the chat, and Varna will also send you a follow-up email to give you a chance to do that. So this research is being led by Dr. Matthew Mason and Associate Professor David Lang, who are both from the School of Civil Engineering in the University of Queensland. The project's a collaboration, so they've got a large and a multi-talented team together that covers researchers from the University of Queensland, James Cook University, University of Technology Sydney and Risk Frontiers. But I'll hand over to Matt and David to introduce the team and to introduce the project to you. Thank you, Matt and David.
Thank you, Blythe. So as Blythe said, so we were very fortunate enough to be sort of awarded this project, which I think is probably going to be, well, it's going to certainly be a very interesting project to do, and we're hopeful that the outcomes will be quite useful. It is a collaborative project across the University of Queensland, University of Technology Sydney, Cyclone Testing Station at James Cook University and Risk Frontiers. And I'll introduce the specific people a little bit later on in this talk. And I think probably I'll also provide a bit of context behind the change in name, I guess, of the project. So we sort of responded to an EOI put out by NHRA for the project specifically focusing on cascading natural hazards and their impacts. But I think probably where we sort of thought things were that many agencies we know have their own internal network and risk and resilience modelling capabilities, but there is actually not a great deal out in the public literature that would allow some of the more open research to get done. So we really thought that the first step was to look at not necessarily to focus on the cascading and compounding effects at this stage, but to first of all focus on getting a set and a suite of publicly available models for how you sort of model the impacts of natural hazards on network infrastructure, and then sort of further down the line we'll go to the point of trying to look at more of the compounding and cascading effects. Certainly not to downplay those things, but I think we kind of need to run before we, so walk before we run, not run before we walk, right? Okay. And today, myself, I'm Matthew, and David Lang, my colleague, will also talk a little bit. If I can get it right. There we go. So the context of the project is sort of threefold, really. So we want to, first of all, establish the context to understand extent of both direct and indirect impacts on infrastructure due to natural hazards. And this is really around the idea that these are very, very complicated systems. So really even just contextualizing and really across multiple networks to try and do this in a formalized or a similar manner across different networks, I think is quite important. We then want to develop or really expand upon existing methods for understanding the impacts of the natural hazards on the infrastructure and really flowing through to losses. So it's one thing, and this is one thing engineers tend to do quite well, is we understand what is breaking or what is failing and why it might fail, but don't necessarily follow that through to what is the actual financial consequence of this. But this is kind of what we want to be able to do here. We want to go through to that point so that decision makers can use that information when they want to start looking at things like investment in resilience. And which leads into the third one, is we want to try and build that framework for how you could assess resilient building activities or modifications to networks and determine whether, yes, indeed, this is going to reduce the losses or this will reduce the risk and therefore is a good investment. The point there is that the term infrastructure can mean many things, but what we're focusing on here is really public infrastructure assets, which we'll look at a bit more. So the kind of tasks we've set out to do within the project, and this is kind of stemmed from the initial request from NHRA and our subsequent discussions with them about the way we see the project working, is firstly, we really need to get back and review what is available. And really, we want to focus on what is available publicly. But we know that there's going to be much, much more than that. So we need to work quite closely with stakeholders like yourselves to understand what is going on within agencies or infrastructure operators. What information do you have? How does that relate? How similar is it to what is available publicly? And how can that maybe be bridged? We then will move on to develop the methods for estimating direct will be the first step there, looking at the direct impact. So understanding if we have an event, if we have a flood of given intensity, what of the infrastructure assets will be broken? So that being the direct impact of the hazard on the network. And then really trying to understand how can we then extend that to look at some of the indirect or the subsequent losses or damage that occurs across a network, but also between networks when these types of things happen. And really the indirect one is in many respects an unconstrained problem. It can go multiple steps down the line and still be an indirect impact. So we're going to have to work quite a bit on making sure that what we class in that indirect impacts can be constrained. And this, I think, we'll also be wanting to work very closely with the stakeholders to determine how far up or down chains do we need to go. Once we've developed those models or those estimation tools, we then want to take a series of utilization case studies, or what we've called proof of concept case studies, to sort of showcase how some of these models we've developed work, and potentially be then doing some then we will be doing some cost benefit analysis, looking at if we say make changes to A, B, and C, what's that going to do for the subsequent impacts for that given event. Now, this could be done really in a very quantitative manner through a full risk assessment. That's not what we're trying to do here. Really, what we're trying to do here is develop the vulnerability or the impact models and then showcasing how they work. That could then later on be taken into a full risk assessment model, but that won't be necessarily done here. Using some of the lessons we get from those case studies, we want to develop the conceptual framework for cascading and compounding events. And really where that's going to stem from is that many of the estimation tools that we'll develop will be sort of working on the assumption that when something fails, it's going to fail from a given state, which would be its operational state. Whereas once you have compounding or cascading, that assumption is no longer true. So you're going to start impacting something that's already been impacted. And that becomes quite a complex problem. And we really want to see where do any of the models that we develop effectively break when we kind of make that assumption, or where does that assumption become void. So we won't necessarily aim to achieve all of that, but we do want to outline where that might need to be fixed. And this kind of feeds into the last task, which is outlining the sort of scope for future research in this area. Right, so the project itself has three main areas of research, three tranches of research that we're sort of proposing here. The first being network mapping, and we'll talk about each of these in a bit more detail in a minute. The second being damage estimation and the development of damage estimation tools. And the third is the utilization case studies. Okay. The hazards that we're going to work with are flood, wind and storm, and fire. So really the three big ones. And the networks that we're looking to work with. So at this point, and this is certainly something we're more than happy to discuss within the subsequent discussion, is the power network. So both transmission and distribution, the potable water network, and the third one that we're looking at is either telecommunication or transport. And we'd certainly value your thoughts on which would be most valuable out of those two. Now, the study region that we've decided to work on, and sort of, I guess, the overarching objective here is that we develop something that can be applied anywhere, right? That's an overarching and probably unachievable hope. So what we've sort of done is, well, what we've said we're going to do is we're going to focus development of models and estimation tools in Southeast Queensland. And the reason for this is it increases the opportunity for the research team, and Southeast Queensland being where much of the research team is based, to have face-to-face engagement with stakeholders. We can leverage and also build upon existing connections we have in the region, and also this will reduce the project cost. And this is a practical one. We don't have the funds to be flying all around the country to have some of these meetings. However, what we very strongly would like to do is ensure that any frameworks that we come up with or the approaches that we develop are largely region agnostic. So it might mean that the actual structure of a network or some of the interconnections that exist would be different in Southeast Queensland to a different area. But the way that they get brought together within the modelling framework should be similar across. And again, this is where we're going to lean on the stakeholders a little bit, and we want to make sure that as we progress through the project, if we kind of start becoming a bit too localised to this region, you kind of tap us on the shoulder and say we need to kind of broaden that, or that wouldn't work in our area because of X, Y, and Z. Right? Okay, so I think I'll turn over to David for a minute, who'll give a bit of an introduction to some of the proposed work we're going to do around network mapping and give us some examples of how that might go.
Oh, thanks, Matt. And hello, everybody. I noticed there was a question in the chat. I guess we'll take that at the end as part of a broader discussion. So talking about network mapping, so what we want to do is to work with stakeholder organizations, so with people who are represented on the call today, as well as some other organizations that we may identify as well. So that is to understand and to map the current networks, and importantly for us to develop an understanding of what your current knowledge of vulnerabilities within your systems actually is. We're interested as well in understanding your knowledge about interdependencies with other infrastructure systems as well. So whether it's our logical, geographic, physical interdependencies, we're interested in understanding what your level of knowledge and your ability to deal with those is at the moment as well. I know we want to use network maps, so maps of the physical network as well as causal network maps to understand the flow of the damage within and across the networks and the hazards. So the best way to describe both of those 2 points is actually with a couple of examples. So if you could go to the next slide. I assume I don't have control of this. Yeah, okay, great. So this is an example of a tool which we've been working on here at UQ, which is being designed for risk assessment to enhance and inform risk assessment practices. We call this causal network topology analysis. The idea behind the tool and the background behind this tool is essentially that if you've got a HAZOP, any risk register, you will have literally hundreds and hundreds of risks or risk events which are identified in that. And it becomes very, very difficult to identify for all of those risk events, looking at them individually, the relative importance of many of those events. What we've recognized, or what we're recognizing with this methodology, is essentially that each of those events, which has a cause and a consequence, those causes and consequences are events in and of themselves, and they repeat elsewhere throughout the network. So what we have got is a little bit of software that turns a risk register into this type of a causal network. And by studying, let me go back a bit, sorry, and this causal network, within the causal network, each node in the network is a risk event. And that could be, for example, failure of an asset within an infrastructure system. And then each of those links in that represents a causal connection between two events. So by looking at the topology of this causal network, which is shown on the screen on the left, we can actually gain a lot of insight and a lot of information that you can't easily glean from that risk register there at the moment. So for example, we can identify whether or not there are missing events in the causal network, which I'm showing on the left. You can see that there are 2, 3, 4 sub-networks which are not connected to the main network. Just by looking at this network, you can identify already that there are probably missing links between those sub-networks and the main network. We can also identify if there are missing causal relationships between events. We can identify events which are originators. We can identify events which are final events in a system. And we can use that information as well to tell whether or not the context of the risk assessment is complete, or whether or not we actually need to go further upstream or further downstream within that risk assessment. We can also look at the robustness of the network. And the way that we do that is by ranking the events within that network based on different topology metrics, and starting to remove those events to look at how many of those risk events we actually need to take away, to remove, to mitigate, in order to prevent the entire causal network from actually occurring. So it's a way of looking at how easy it is to break apart and how easy it is to manage the risks in this kind of interconnected network system. And what we're proposing to do is to take this, which has been developed for, we've applied it to various applications in, for example, the mining sector, or within fire safety. We want to take this approach and apply it to networked infrastructure systems. Use this to essentially identify the relative importance of the different nodes or the different assets within those infrastructure systems in terms of preventing those kind of cascading or compounding effects. Do you want to go on to the next slide? Yeah, and I just put this in as an example of something which would be very useful to allow us to expand that, or basically maybe to understand a little bit better those impacts beyond those 3 infrastructure systems that we're really focusing on. This is an example of an output from a European project which I was involved in a few years ago, where we took 50 examples of large-scale incidents which had occurred around the world, and we looked at different pairings of originators and dependencies between infrastructure systems where there was that kind of interdependency. On the columns, on the column is the originator, and on the row is the dependency, and basically the size of the bubble indicates the number of times in those 50 incidents that we reviewed when, for example, an incident which impacted on power supply had a secondary or cascading effect on, for example, telecommunications, or on business and industry, or on the public as a system as well. And so this type of tool gives us, I think, an opportunity as well to maybe validate some of what we're seeing if we're trying to apply that causal network topology analysis. It also gives us an opportunity to expand a little bit our analysis beyond those infrastructure systems that we're looking at in a lot of detail.
Thank you, David. Okay, so I guess the second main task within the project is the development of the damage estimation tools. So really what we're trying to do here is to develop direct damage tools, and we'll make these open source. And this will be done either empirically by looking at, through discussions with the infrastructure operators, understanding what failed and under what conditions. We can do this empirically, or we can go down the line of more a pure engineering line where we say, okay, we know what a transmission tower or a distribution pole looks like. We can model the load on it, look at what is required to fail the structure, and then build that into a model. Now, neither of those does everything perfectly, so it's in the end, it'd probably be some combination of the two that we'll do. But really, in the end, what we're trying to do is link some type of hazard metric, be that flood inundation level or wind speed, to an estimation of loss. Right. So we want to compare, well, first of all, through the review of existing literature and existing models, we'll be able to identify what already exists and what might exist in other regions of the world, and then we can compare whatever we come up with what is done elsewhere, or if we decide that, okay, what's been done in the UK, for instance, might actually be directly applicable here, and there we can just port a model over. And then what we need to do is kind of work together with some of the information from the network mapping to try and understand the interdependencies, which will help us understand and help us try and figure out how we incorporate some of the indirect losses in there. So we need to understand how the flow of damage occurs from one point to another and across networks, and then we have to think about how do we put that into sort of a modeling framework. So just as examples of work that we've done before, this is not infrastructure. This was where we were looking to develop loss estimation tools for a specific industrial building here to flood inundation. And what we did was develop an engineering model of the structure itself, look at what are the vulnerable components of the building. We're able to then develop specific models for the reliability of each of those components. And the figure on the bottom is just showing how, for inundation depth, the damage to a particular thing, and this was the cladding on the building, how that was impacted. And the damage ratio here is just the amount of it that was failed under a given inundation depth and flow velocity. We can then sort of use some information about how much it costs to replace that type of that component of the structure to build then a loss model, which allows us to then relate building loss ratios, this is really the percentage, the replacement cost divided by the cost of the building. We can convert that through to something, again, based on the hazard metrics. And the way we could do this for infrastructure networks is you do this very specifically for individual components of the network, and then you have a way to bring them all together so that you're looking at the network itself rather than an individual asset. And where we sort of started doing this was David and I had a PhD student who's just recently finished, who developed similar types of models looking at relating the wind speed that transmission networks see and the probability of different damage states, or the probability of failure. And we're able to, again, develop these sort of quantitative models that allow you to bring that together. Some work David did, again, through some of the European projects that he was involved with. We have just an example on the left of a recovery model for the water network in Portugal following earthquakes. And here again, this is where we're able to look at using engineering-based models to look at how the flow of water goes through the system, the repair times needed, and you're able to build this in and then model it as such. And through doing something like this, you can develop a tool that allows you to look at, given different periods of time, what is the percentage of the network that's back up and operational. And you can do that in different capacities. It doesn't always have to be binary of doesn't work does work. There are different states things can operate in. So I guess the third component of the project is the development of the case studies. And what we're proposing is that these are not necessarily historic case studies, but hypothetical case studies. My personal view is that these, I think they work well when they're sort of based on events that have occurred in the past, but not necessarily forcing them to be exactly those events. And what we're going to first do is look at these for individual hazards. So we might develop a model for flooding. We'll develop a scenario for flooding. But then we can start looking at bringing those together and putting interconnected networks into individual hazards. We want to then develop a case study that looks at the retrofit or resilience building. So within the damage estimation tools, there'll be characteristics of the individual assets within a network. We might say that we do, we put a couple of extra reinforcing connections into a transmission tower, which will give it a bit of extra strength. How does that then flow through if we have the same event coming through? And using that, you can then assess, well, how much does it cost to do that to a transmission tower, and what are the subsequent flow on improvements that you get in, or the reductions in the impact that you get. So we'll then look at bringing the compounding events in there, and we're going to look at a series of events occurring one after the other, and we're going to look to see, well, where do some of the models that we develop, where do they start failing? So for instance, if you leave a certain period of time, let's say a year between flood events, what will happen to does everything get back to where it needs to be? And then we can again assume that we're in a undamaged state, or is that not going to be the case? And then finally, we want to kind of look at what are the research needs going forward. And here's just, again, an example that we've done in the past. This was actually work done for the Bushfire and Natural Hazard CRC a few years back, where we came up with a hypothetical scenario that was sort of perfect on Tropical Cyclone Dinah, which was an event that sort of came through the region but didn't quite make landfall in the late 1960s. We modified it a bit, so the kind of red cyclone marks is what we ended up doing in this case study, in this scenario, sorry, and the solid grey line is just where the storm actually went. We've running that event through, we're able to look at the mean damage ratios over large areas, and we also did this for displaced population and a couple of other things as well. And then where I think that some of these scenarios are really quite useful is also looking at the sensitivity of some of these things. And one that I always found quite useful was if we shifted the track only sort of a couple of tens of kilometers left, sort of west and east, the figure on the bottom shows the distribution of expected displaced persons, and you're sort of doubling the extent of damage that you might get just by making very small changes. So here you can start looking at the sensitivity of some of the impacts that you might expect for given events. Right. So the research team, as Blythe mentioned earlier, is made up of researchers from the University of Queensland, Risk Frontiers, University of Technology, Sydney, and I forgot to put David Henderson on here from the Cyclone Testing Station. I knew I'd forget someone from the team. But anyway, sorry. So yeah, I suppose David and Ben are really going to be in charge of the first tranche of this work in the network mapping. Myself, Hal, and researchers from Risk Frontiers will be looking at a lot of the damage model estimation, and all together we'll be looking at the case studies. The folks over on the right here are sort of really on the project in largely an advisory capacity. So Paula Jazabkowski is a professor in the business school here whose expertise is in disaster insurance. And so, as you'll probably all be aware, I mean, the way we finance a lot of repair and rebuild is through insurance, maybe not so much for infrastructure, but that doesn't mean it's not necessarily going to be something that's not dealt with in the future. So Paul is going to bring sort of that context to some of what we do. Mark Stewart's a professor at UTS who specialises in cost-benefit analysis and resilience of infrastructure. Mark Hickman is a professor here in the school that's within the transport engineering group, so is an expert in transport network and their resilience. And Yuri Karlovchek is another infrastructure person within our school that's going to help us in that area. And the person not here is David Henderson from the Cyclone Testing Station, who is an expert in structural vulnerability, particularly the vulnerability of housing stock to wind and storm events. The project management committee is at this stage made up of Blythe, David and myself, Jane Sexton from QFES, and Ella Harrison from QRA. And I've never met Ella, so I'm hoping I did get the right photo for her. I think with that, I'll probably leave it. And I think we're very, very happy to take any questions you might have, and looking forward to some discussion about how people might think we can improve the project or how they might be able to be involved.